Hi everyone, welcome back to another Menlo Community Call. It's very good to see everyone here. I'm Mimi and I'll be your host today. And whether you've been with us since the very first call or you're just joining for the first time, thanks so much for hanging out with us today. And as always, if you can't stay for the whole stream or you're just catching us later, no worries at all. Every stream gets uploaded to YouTube afterwards. So you can always come back and watch it whenever it works for you. And if you're watching this live, come say hi to us in the chat. We're very friendly here, I promise. And we'll be keeping an eye out on the chat throughout the stream. So if you have any questions as we go, please let us know and we promise we'll do our best to answer all of them. So for anyone who's new here, here's a quick idea of what these community calls are about. So every week we like to sort of pull back the curtain a little bit and show you what we've been working on. And that usually means walking through what we built, what we potentially broke, what we learned, and where we're headed next. And today, here's what the lineup looks like. You may notice we don't have our usual hardware team here, and that's because they're busy cooking up something very special behind the scenes. And we will hopefully be able to share more news with you later on. But instead, this week, we'll share a few broader projects happening across the entire company, and we've still got plenty to show you. And we'll start with software team. Then we'll dive into what our brain team has been working on, move over to robot systems, share some fulfillment updates, and we'll wrap things up with careers. And as usual, if something catches your attention while we're talking, again, just don't wait until the end and just drop your questions into the chat and we'll answer as many as we can. Okay, so let's just get straight into it. And I'll pass on to our software team.
Hey, good morning, good afternoon, everyone. Today I'm going to share with you our progress in building our platform client app. But first, for anyone new here and to refresh some of your memory about what I shared last week, we proposed a security architecture for our robot called robot cycling or RSL in short. In this architecture, the server, Menlo server or any other relay server, I got a server. It cannot fork cannot fork or modify or like create any unverified command to control the robot. So it ensure that even if the server is compromised, the attacker cannot control or cannot move the robot. And we build that into our client app, which I will happily show you now. Okay, so this is a desktop version of it. We create a simulated CPU, the one that is running on the Asimo hardware. Right now it is offline. So let me start it. Okay, so you can see the green dot here, meaning that it is online, and we can start connecting to it. Please keep in mind that this is CPU emulator. It doesn't have a body, so that is something why you're seeing just a simple dot here, showing the green one is where you think that it's facing, and the blue one is like it chase. This one is paired with this device, and the two we communicating using our robot cycling protocol. Yeah, we are going to integrate it hopefully with the real robot soon, maybe tomorrow, maybe the upcoming week. On the desktop, you can also see other settings as well, which we are working on. You can also back up your recovery key. which you can later on import into other device, or you later on you can also generate some key as well here to start controlling the robot from the SDK. Let's see the mobile app. This is very much similar to the desktop one that you can see here. So switch the theme. It's not working very well yet. Yeah. And let me also show with you some of the thing that my teammate did. He's connected the PS5 controllers to the desktop client and start controlling the robot. And yeah, I think that is for me to share with you today. We are working on a lot of things behind the scene, and yeah, hopefully next week we can share with you a lot more fun stuff. Yeah, thank you. Yeah. Back to you, Mimi.
I think there's a question from Nicole, actually. Do you want to address it?
Yeah. Asymmetric encryption. Yeah, let me open up the link again. I don't know why my laptop is lagging.
I think your laptop has been working very hard.
Yeah, so it is running a lot of simulation. Yeah. So there's some spec you can look at, and the link is shared on Discord. I will try to find the link right now and pass it here. We are first. I need to clarify that we are not doing encryption yet. This is not part of the robot cycling spec. So the command when it's sending between the robot and the client is not encrypted. But the protocol we are using, we ensure that we use the key to sign another key, so that is certify the other key. It's not like encrypt the content of the data, if it makes sense. We do use some encryption to back up the key to our server with passphrase. Yeah, and I hope that answer your question. Yeah, we use some algorithm. I think Argo ID or something like that. Yeah, to encrypt the backup block of your private key to the server with a strong passphrase. Yeah, so the multi it allows you to so it allow you that if you lost your device, you can still enter your passphrase and you can still continue using your account in another device.
I think there's another request. Whether we want to talk a little bit more about the RTL spec, and maybe the community has any feedback or maybe ideas. Is there anything you want to share, James? Or we can save it for another time.
Yeah, so please reach out to us on Discord. We would love to discuss with you in depth about our security proposal. Would love to really love to the community to share that it. Yeah, I know that a lot of people in our communities like have been working with it in a while. In the field for in the security or in the hardware field, and we would love to hear a lot more from them. Yeah. So another question. So we um, we still have an account login system. This is for you to register organization, um, setting up a permission control the normal uh, robot access controls and like organization and team stuff. And it's also allow us to verify that you particularly store the all the key backup and everything, and also allow the hosting of the kit so that the robot and the device can connect to each other. So account login is still mandatory. We could make it optional in the future, but I think for version 1, we still keep it. Would it support multi-factor authentication? For login, right now we don't have it yet, but it can be enforced. For key 1, I'm not sure if you for the key 1, we might also do that so that like you need to enter your biometric or your 2FA to be able to download the recovery recovery backup on the server. Yeah, but it's still very early. We are still refining the flow so that it balance between security and user experience.
Okay, I think that's all the questions for now. But again, please just feel free to drop more comments, feedback, ideas, anything into the chat. And in the meantime, we'll move on to Ishnet, and we'll just come back to more questions at the end if you have any. Thanks, Jane.
Thanks.
Hi, good morning, everyone. Last week I think Jackie spent some time talking about what we are trying to build with the brain team and what we're thinking about along the lines of a large physics model as the eventual goal. And this week we actually did some experiments to prove certain hypotheses we had in the initial phase. And we also consolidated all our learnings into a paper. And I'll be walking through the main learnings and the motivation behind what the experiments we conducted in this paper are, and we hope to release it by the end of this week so that the community can read through the paper, look at the open source repo, and build on top of it, give us more ideas, tell us if we're doing anything wrong or not. So the motivation for why we actually even want to build a multimodal embedding model for robots is because like when you pick up a cup, or when you're filling a glass, you just don't rely on vision, and you just don't rely on like pixels. You rely on the weight of the glass. You also rely on the sound as the glass is being filled up. And so this actually shows us that this different senses are actually entangled in a way, and you need to rely on all these senses to actually be able to do a realistic task in the real world. And vision is just one sense among several, and it's not the most important one for manipulation. And now if you think about it, how do every other robot learning system work? They usually run a camera through a big vision model, and then they get some form of representation, and then almost as an afterthought, they staple the other sensors. So they have some audio which is encoded, they have some force which is encoded, and they also have proprioception data which is encoded. But the core understanding of the module in most of the systems nowadays is just pixels. And so when the system relies too much on pixels, everything that a robot does downstream is basically limited by what its encoder captured. And so if information about force never makes it into the encoder summary, then no policy, no world model, no predictor can actually reason well and get the robot to do something really important, or actually get it to fulfill the task. And so we actually even verified this in one of our experiments, that if we just encode vision, can we actually get anything about the force in the after the encoder? And we actually cannot. So if we just encode vision, you actually don't get any information about force. So vision only encoder is like fundamentally and structurally blind to one of the most important signals in manipulation. And so what our motivation right now is that we want to build an encoder that takes in multiple modalities. It takes in vision, it takes in proprioception, it takes in audio, it takes in force, and then it fuses them into some form of like single shared summary. And that makes the foundation actually reusable for whatever predictor, whatever DIT, VIT backbone you want to use later on to actually reason about the task. And then eventually you can decode it into action chunks and the robot can actually execute it. So I think the main things we're sort of contributing in this paper right now is that one, vision has VIT or clip as the encoder, language as LLMs, but robotics still sort of uses these separate encoders to actually encode all these different sensor modalities. What we are saying is that we have to build a multimodal encoder from the robot's perspective first, and also because our robot in this case is open, we control all the sensors, we can actually understand the robot better from a hardware perspective as well. What sensors are the most cheap, what sensors are the most accessible to put on a robot, and then use all these sensors and use all the information that the robot exposes, and package it into a very good, very compressed latent, and that will actually help a lot of the downstream tasks to actually reason about whatever the robot feels, whatever the physics the robot experiences, and reason about these tasks well. And so what we try to do through this paper is we have a robot first multimodal encoder, and we're able to show that cross modal fusion works. We also were able to show that the data set we use, the encoder is actually embodiment agnostic and performs better than sort of specialist encoders, and that vision only latents cannot actually recover the force that the camera cannot see. And we also proved some downstream uses of the frozen encoder. So we were able to show that an encoder can actually be used for some safety scenarios, as well as the basic principles of an encoder. Is it even able to reconstruct vision properly? Is it able to reconstruct robot state properly? All these things are also preserved. And so when we start with this project, we have to think and ask ourselves a question, why an encoder and not just a policy directly? So a policy is trained for only one task, and an encoder is trained and it can be reused by everything. So that if the representation is good, you can evaluate it cheaply with a small probe instead of retraining the whole robot policy. So the encoder is actually the main leverage point that will allow a lot of downstream tasks to come and flow very smoothly. And so why self-supervised, right? Robot data has no labels at scale, and it's really very hard to annotate multiple different modalities in the robot data sets. So you can't, expect someone to annotate millions of frames of force, vision, audio. And so ideally we want the encoder to teach itself from the raw streams. And the way we can do this is, with self-supervised. And why not, reconstruction or using autoencoders? So one thing we realized with that is that with autoencoders, you're sort of memorizing every pixel and you can just sort of reconstruct it, but you're not really understanding the reasoning behind it. And why not contrastive losses, or just make audio, video, and force equal? When you do that, you're just sort of taking the intersection point of all the different modalities, and you actually lose a lot of information. And this is what a lot of research is currently doing. They basically take audio, they make it into a spectrogram, and they basically treat everything as almost vision. But by compressing it into a form factor before it's actually encoded, you lose a lot of raw value from that sensor itself. And we built specifically on LeGepa, which basically has a simple mathematical trick in its loss function called sigreg that basically proves it stops the model from cheating by collapsing everything to one point. And so this actually allows us to take advantage of the LeGepa and the whole JEPA architecture to prove a concept with the encoder. And so the key idea over here is, you can see in this figure, is to fuse wildly different sensors. We have to put them into some form of common language. So we just turn every single sensor into a small token where it has the value, what it measured, the pixel patch, the joint angle, force reading, the audio, which sensor it came from, and also where is it, so it's spatial embeddings, and also when, so we can actually encode each different sensor with its native sampling rate using some form of real time step. So the encoder also respects the time. And so one neat trick in this is that instead of truncating all the sensors, we sort of use a masking approach. So different robots may have different joints, some may have a force sensor, or they may not have a force sensor. So instead of designing custom input for each robot, we use one fixed layout and just mask the other parts of a robot, parts that the robot doesn't have. So it actually helps us to make the encoder feel like if there's a missing sensor, it's basically that it's masked. So the model is also robust to dead sensors by construction, and one encoder can actually work for every robot. And so the main architecture we are actually experimenting with is this cross-attention fuser, where we take an image and we put it through a frozen pre-trained VIT or vision model, and then all the tokens after that go into this perceiver architecture, which is basically it will ask summary questions that read over the whole bag of tokens, and then it distills it into a very compact latent. And so there's a question: why would you use a perceiver and not just a giant transformer to learn the attention across the latent? For the perceiver, it doesn't blow up as you add more sensors or tokens because the summary is always in the same size, no matter how many sensors are actually coming in, which is what exactly lets the masking handle different robots cleanly. And an important detail for this is that at test time, we feed the encoder vision only. So we hide motor and force, and we are able to actually derive from that the latent has actually learned good information about the force and the joints just from the pixels alone. So if you don't have those sensors, if you just deploy with the camera, but the latent is actually trained on multiple modalities, even with the camera it's sort of able to mimic those other modalities as well. So the way we actually train is, let me show it here. So this is the main losses we use in our training objective. And it's basically very simple, where we just want to hide one modality and predict its meaning from the other two. So what we do is we can hide the force and predict what the force should be from vision and joints. We can hide vision, and then we want to predict what the vision can be from the joints and the force. So this actually works because a shared multimodal encoder without this cross-modal sort of losses actually does worse than single modality models, because it just combines everything and concatenates everything together. And the cross-modal prediction is where it actually makes the fusion work. And it makes the latent really compact, really compressed. It makes sure each modality sort of entangled with each other. And again, I'll talk about the results we actually the experiments we conducted and the results we got that actually prove some of our points here. Yep. So from the results, we were able to prove that we can actually train one encoder for all robots. So if you look at this here, we can actually train an embodiment agnostic encoder. And this is where we are able to show that the encoder trained on all the embodiments actually outperforms the specialist encoder trained on all. So what we did for this experiment was we trained it on 4 different robot arms at once, and we asked whether specialist encoder will do as well as whether generalist encoder will do as well as the 4 specialist encoder trained on each robot embodiment. And we were able to show that actually the generalist robot is able to learn more cross embodiment and cross modal behavior in general rather than a specialist encoder. And the second result we got was that let me show this figure. Yeah, this was the main result we got as well, is that we were able to actually take the vision only latent to predict force torque better than raw vision features on every robot that has a force sensor. And this means that fusion of the cross modal features actually is able to deliver where it should, where the camera is blind, and where the camera doesn't have information about the force, but it's actually able to predict force and other modalities better. And then we also had some downstream experiments where we try to do some form of safety detection on the encoder, where we just wanted to know that if the robot state is not what the vision expects, can the model's cross modal prediction actually spike when it sees like invalid states and sees if the robot is not doing something safe. And then we also did some basic decoding on whatever the encoder was able to train. And we just wanted to see, if a tiny decoder can recover joint state from the latent, as well as we used this diffusion model called PixNerd to just see if we can actually just decode back video from the latent as well, and whether a small generator can redraw the camera frame from the latent, showing that the 256 dimension latent is actually quite intelligent, and it has actually retained a lot of information. And so with this main experiment, one caveat is that okay, it's still single time step, so it's not actually learning anything across the temporal phase. And what the next experiment we want to design is that we want to do it across the temporal space, and see if the model is actually able to learn in time, not just across modality. And so what we will do for this is that, because our each sensor has a different sampling rate, and we can't just concatenate them to one sampling rate and then just fuse them together and put them into the perceiver. What we do is we basically associate each sensor stream with its real timestamp, so almost like a temporal embedding, and then we can fuse the streams across time at their native rates, so we don't have to resample, and we can use the same architecture. So you just basically switch the when part of the token, so you just associate a time with each sensor stream. And this is the path from like a static encoder to a genuine world model, where you're able to predict the future, reason about dynamics, and they can condition on actions later on. And so this is what we'll be focusing on eventually. And then some limitations of a method so far, and the experiments we are doing, because this is still quite in its nascent stage, and we're trying to figure out what will sort of be the best encoder architecture that will actually work on the real robot as well. So the main limitations is, one, it's currently it's single time step. There's no temporal results yet, but this is what we want to do next week. And also it's correlational, not causal. So it learns that the modalities co-occur, but we can't still prove that it's cause and effect. And so also the data set is quite, it doesn't have a lot of variance. And eventually what we have to do is, once we are able to train a VLA on the arms and the robot we are working with, we'll be able to actually prove the encoder's concept better, because we'll be using the exact data we will be using to like deploy on our robot, rather than just using a general data set which is available online. Yeah, if you have any questions you can ask in the chat. But this was basically the conclusion for whatever we're training with Kepler encoder, which is basically a robot first multimodal encoder that will take different modalities and actually make the latent really, really smart, so that whatever downstream tasks you have, so after you have the encoder, whatever predictor you want to train will be actually able to reason very well, because a lot of information is intelligently compressed in the latent itself. Yeah, that's all from my side. Thank you.
Thanks, Ishneet. I think there's a question from Richard Franklin. Maybe you can share a bit about data.
So the data we used is this open source data set called RH20, which is basically a data set which has multiple modalities. So in that data set, there's audio as well, there's force sensing data, there's robot proprioception data as well. And we just wanted to quickly prove a concept with a multimodal encoder. So we just took a data set off the shelf.
Okay, thanks, Ishneet. I think we can move on to Salim next.
Hello, everyone. I'm Salim, one of the members of the technical staff here at Menlo. I think this is one of my first community calls here. Today, actually, we want to go through a little bit of like what we call the Asimov Manager, which is a new form of like software that we are going to develop. As you guys know, like we have a Raspberry Pi that is connected to a LoRa controller, which we call the Robot Processing Unit, the RPU. The RPU is basically that part that runs the locomotion policy, that talks over CAN to the motors, that does all the real-time inference and real-time control. And the Raspberry Pi is basically the one that is connected to the network and can set up your overall computer, like overall robot, sorry. And while we were like working with that, we realized that it would be great to have almost like a router logging page where you can log in into your robot from time to time. This does need to be logging every time. And then you can basically set up all the different services. You can set up, security keys and basically start and stop the different services that are running on a robot. And this is where the Asimov manager was born. It's basically a very minimal control and config service that runs on the robot, ideally on the Raspberry Pi. This is how we going to do it. So how it actually works, there are like a lot of different like systemd services running on a robot. There is the systemd service of the Asimov firmware, the Asimov API, which is documented in the manual online. And, we are basically trying to create a CLI where you can basically check the different status of this. So you don't need to be logging into the RPU directly. You can actually be just using everything on a Raspberry Pi and get the entire information about the configuration of the robot per CLI commands, pretty much. So you don't have to touch the code. You don't have to open different, shell files or like bash files or any like config files. You can literally just use this API, this CLI, sorry, and you can basically start up your robot very simply. And how it actually looks, and I think we should also discuss a little bit about this architecture because this is quite new. So as you guys know, again, we have the RPU, which is where the Asimov firmware runs. The Asimov firmware is a real-time application. It runs like on real-time Linux. We have been verifying it over and over that it meets the timing requirements to perform the locomotion policy, perform the communication over CAN. Hence, we want to make sure that this device is basically not, responsible for networking, for like connecting to different clients. We do want to separate this, as this is the real-time piece and runs with very high priority on the entire system on a different board. That's why we basically disconnected this actually also electrically. The Raspberry Pi is the device that is responsible for like connecting to the network, running your individual applications, your web servers and everything. The Raspberry Pi is also running the Asimov API. So the Asimov API is pretty much, maybe you guys know from the Unitree world. The Asimov API is how you can talk to the robot internals. You can basically ask for states of the different motors, states of like temperature of sensors. You can pull anything you want that is robot specific. And you can also run and control the robot through the Asimov API. So when you would run this on the cloud, you would technically just talk to the Asimov API, and your LiveKit SFU, which stands for Signal Forwarding Unit, would run on the cloud. But as we like develop things locally and test things offline, we actually thought about just moving the LiveKit SFU also into the Raspberry Pi. Since the LiveKit SFU is actually a very lightweight program, it can run on a very small, even microcontroller these days. So the LiveKit team has done very good work there. So we actually pull the LiveKit SFU into the Raspberry Pi during the setup. So you can actually mimic how you would connect to our platform in future. So the Asimov API is then basically talking to the LiveKit SFU, which then talks to your client application over WebRTC. And this can run anywhere you want. This can run on your computer. This can run on your toaster, technically. So, as you guys can see, we have like 3 services we need to set up with the correct sequence. There's a LiveKit SFU, there is the Asimov API, and the Asimov firmware. And to set this up in the correct sequence, you need to run this, like you need to first run the Asimov firmware, then you need to run the Asimov API, then you need SFU. And each of those components actually has a check that, like a heartbeat check, that its neighboring component, LiveKit SFU or the Asimov firmware, is alive. So there are checks all around to make sure that the system is properly set up before you can actually operate it. So there is a heartbeat between these two guys. There is a heartbeat between these two guys. There is no heartbeat here because I think the client application can always go down. There's no reason to basically kill the system. And to actually set up all of these different services, there is the SMOF manager. The SMOF manager is basically this one component that I showed previously, where you can, it's almost like a router page. You can log in to a different port just locally. It doesn't need to be only, as long as you're on the same Wi-Fi, I guess. And then you can basically make sure if all the components are already running. By default, technically, when you turn on your robot, all these services, they should come up automatically themselves. The SMOF manager is really a one time when you buy the new robot to set this up the first time, and same as a router, right? A router, when you buy a Wi-Fi router, you set up it once, and if something goes wrong, you can go back to the router logging page and change certain things. So the first time you buy a robot, these services will be offline. Only the SMOF manager will be online. You connect to it, you start the different services. All the different services you can individually test through the SMOF manager API, SMOF manager logging page. And once all is set up, you can basically reboot your system, and from there on, everything will run automatically. So there is that's the idea behind this. So the SMOF manager is really first time usage, and if something goes wrong, you can check certain things. As well as when you say, okay, I want to change my LiveKit access token, same as you want to change your Wi-Fi password. You just log into the router page, you enter the new data, your new password, your new secret key, and then basically you reboot the system and it should automatically pick it up. So the web UI, I think we need to do this a little bit bigger next time, but the web UI is actually very simple. You can just see the different services, and we kept it very simple. We kept it like, we had made sure that the services itself have most of the logic, and we don't have like a mesh of a lot of services. So there are just really 3 services that are running to operate the robot, the locomotion policy, connecting to the cloud. All are just running to 3 services: the LiveKit server, the API, and the SMOF firmware. So in the dashboard, you can see if they're running, the state. You can see if you want to auto start them in the beginning. You can restart them. You can stop them. You can set your password. And this is almost like the router/config page actually looks like. So yeah, I think this is pretty much it. I think we're gonna launch this soon. I think this will come online as well as open sourced. The team is just preparing this right now, cleaning up the code base. So, and then we should be able to open source this, and if anyone is interested to make this more user friendly or better, feel free to just contribute to the open source repo when it comes up. Yeah, thanks everyone.
Thanks, Salim. I think we can move on to Frank next. And I know that we have questions coming in, so maybe we'll just have a Q&A session for the whole team afterwards, if that's okay. So please continue sending your questions. But in the meantime, we'll move on to Frank with fulfillment update.
Yeah, thank you, Mimi. And I'm Frank, and it's a pleasure to give an update about our SMOF fulfillment status. As I shared last time, we have a vacation unit building this month, and also targeted to deliver our first batch of the SMOF in August. So far, everything is changing, and we are having daily conference call with our contract manufacturing and the key supplier to make this happen. And in the meantime, and we are also working our contract manufacturing to on the delivery service term, and the target is to provide more and more door-to-door service for our customers. And also, we are also working on the BOM update and also manual update. And once it's done, and we'll publish it to our website, and that will be easy for these people that want to build the SMO by yourselves. So actually, a lot of things happened here, and we are working to make SMO and easy available for the whole community. And I believe we have more update in the coming 2 weeks for the SMO, the building status, and also the DTP service. Yeah, that's all from my update from my side. Thank you.
Thanks, Frank. I think we can have Herman do a quick little promo for the new career opportunities we have. Give me a second. Hi,
everyone. Hi, everyone. Very nice to meet all of you today. So as usual, we have lots of open roles. I think end of this week, we'll be also pushing out a role for a world model researcher. So I look forward to meeting each and every one of you, and I look forward to speaking with you guys as well. Have a great rest of the day.
Okay, thank you, Herman. I think what I'll do now is I'll put my our entire team on stage, and we'll just blast through all the questions we have. I know there's a lot to go through, so please bear with me. Okay. I think maybe we can start from the end, actually.
Yeah, I can take this question. So for this, actually, the critique is well that the EPS police statistic is a distributional test, and it almost sort of estimates the embedding distribution. But I think because SIGREG is an anti-collapse regularizer and not the learning signal, I think the temporal dynamics are meant to be learned by the predictive objective. So whatever, like, your action condition, forward prediction loss is at the end. And so I think we try to sort of mitigate this with a design is because we apply SIGREG per time step, not to a time pole latent. So it computes the isotropy constraint on each time step's latent. So you actually never pull across time, and each time step's marginal stays healthy while the sequence is free to vary. Yeah.
I think hardware team isn't around, but I think for the I see.
Daniel, I think I can take this on. So you can technically use the different gripper. I think the connection that it goes into the SMOV V1 arm is like RS252 serial connection. So you can actually, as long as it fits in mechanically, you need to write. I think you need to write your own driver, and that connecting to the SMOV manager or SMOV API. So that is possible, and hopefully that would be also great if you can share this on Discord later on. But I think it all depends on like the gripper interface that goes into the SMOV V1.
Yeah, Ishni, do you want to take this one? Or I think I mentioned in the YouTube comments. I think we will definitely take a look at the data. I think this is the config 7 that is like a different set of either motors or force feedback. And I think Franca might have been the one that had the least data in the data set. So that's also one of the reasons. But it's definitely something that we will investigate. Yeah.
Yeah. Thank you for the thing with the cross-attention approach. Yeah, I think it's definitely needed to actually make sure the modalities learn about each other in the same latent. So I hope it also works on the real robot, but we will be investigating this more and more as we scale up the experiments and actually move on to the temporal phase so we can actually do more world model-like work.
Okay, do we have any more questions? If not, perhaps we can close this off for today, and then we can continue our discussions on our usual channel Discord. So I'll drop a link here so everybody can join our Discord. And otherwise, I think we can wrap up here for today, right? And as always, thank you so much for spending some part of your day with us. If you enjoyed this stream, give it a like, subscribe wherever you're watching, and follow us on X and Discord to keep up with our updates. And we'll be back again next week with more progress and probably a few more surprises along the way. So thanks everyone, and we'll see you next week.